In the previous videos, we talked about order of growth. We talked about different mathematical notations to represent order of growth. Let us now take a look at some common loops that we commonly see in programs, and we need to analyze them to compute the overall time complexity of the programs. After seeing the common loops, we will talk about nesting of loops, loop one after the other, so that we get an idea how to analyze a big program. Let us take a look at this loop. We have a loop for int I equal to 0, I smaller than n, I equal to I plus c. So how much time this loop is going to run? You can see that it's going to run theta n by c times, right? For example, let us take n equal to 10, c equal to 2. This loop will run for I equal to 0, I equal to 2, I equal to 4, I equal to 6, I equal to 8. So how many times this runs? And 10 by 2, 5 times. If n is 11, then also it's going to run 5 times. So we can say floor of n by c is the number of times this loop runs. We can ignore the constants, leading term constants. So we can say time complexity of this is theta n. We can write these constants inside the notation, then we can ignore them also, right? So when I've written theta n by c, I can ignore c and I can say it's theta n. So the time complexity of this particular loop is theta n. Let us now do this second example. We have a loop that begins I equal to n, goes till I greater than 0 and does I equal to I minus c. In all these loops, I have written this theta 1 work. Theta 1, big O of 1, both of them represent a constant value, right? So these terms are always used to represent any constant work, like 100 instructions, 1000 instructions, maybe some addition, subtraction, printing something. Anything that is not dependent upon the value of input n. We are considering n as an input here, not c as an input. C is assumed to be some constant here in these loops. So anything which is not dependent upon n is considered constant in any program, right? How many times this loop will run? This will run for I equal to 10, right? Then 8, we subtract by 2, 6, 4, 2. And after that it becomes 0 and it stops. So it runs 5 times. Let us take n equal to 11. How many times does it run? I equal to 11, then 9, then 7, then 5, then 3, and 1. Right. So it runs 6 times. So we can say it runs ceiling of n by c times. We can ignore the constants, right? And we can say that order of the growth of this loop is theta n. Right? So this function, this particular part of the code has theta n time. Now, if you're wondering about ceiling and floor, you can upper bound and lower bound them by adding 1 and subtracting 1, right? So theta n requires upper bounding and lower bounding, so we can ignore these ceiling and floors as well. Let us now take a look at this loop. Here we are running similar loop, I equal to 1, I smaller than n, but instead of addition, we are doing multiplication. And please remember, c is a constant, not a user input. So we need to find the order of growth in terms of input size n. N is a user input. So how do we find the order of growth? Let's take a look at these examples. When n is 32, how many times this runs? It runs for I equal to 1, I equal to 2, I equal to 4, I equal to 8, I equal to 16, and stops. When n is 33, it runs for 1, 2, 4, 8, 16, and then 32, and then stops. Let us take a look at general value. When you are going inside the loop for a general c, what happens? You run for I equal to 1, then you run for c because you multiply I with c, then you run for c square, you again multiply c with c, then c cube, and so on. So say you run this loop till c raised to the power k minus 1. So where k is the number of iterations your loop runs. So this loop will stop when c raised to the power k becomes greater than or equal to n. And c raised to the power k minus 1 has to be smaller than n because it's running from c raised to the power 0 to c raised to the power k minus 1, where so total number of times it runs is k, c raised to the power 0 to k minus 1, right? So how many times it runs? K times. Now we want to figure out what is the value of k. So c raised to the power k minus 1 has to be smaller than n, and how do you find the value of k in such a situation? You take log on both sides. So you say k minus 1 has to be smaller than log base cn. Then what do you say? K has to be smaller than log base cn plus 1. Which means these many times this loop is going to run. And after that, this value is going to become c raised to the power k greater than or equal to n. And then it's going to stop. So what is this? What is the value or order of growth of this expression? You can ignore the lower order term and you can say it's log n. So the order of growth of this particular loop is theta log n. And please remember one thing, base of log does not matter. If your base is 2, you can convert it to base 10 or any other number, 100 or 50, by just doing some multiplications and divisions with some constant values. And in asymptotic analysis, in order of growth analysis, constants do not matter. Lower order terms do not matter. Constants of leading order terms also do not matter. So we say order of growth of this is theta log n. The base of log does not matter. It can be 2, it can be 10, it can be 100. So order of growth of this particular loop is theta log n. Let us take a look at this loop now. We are running a loop that begins with I equal to n, goes while I is greater than 1, and divides I by c. So c is a constant, n is a user input. We need to find order of growth of this loop in terms of n. I've written some examples here. When n is 32 and c is 2, how does it run? It runs for 32, runs for 16, 8, 4, 2. When n is 33, it runs for 33, 16, 8, 4 and 2. Any guesses? If you take a look at this loop, it's just opposite of the previous loop that we discussed, right? It runs the series with c raised to the power k minus 1, then c raised to the power k minus 2, c raised to the power k minus 3 till 1, right? So how many times it's going to run? You will again take the log and you will say it's log n, right? So order of growth of this loop is theta log n. It's opposite of the previous loop that we discussed. Let us take a look at this next loop. This is the most complex of all. We have a loop which runs for I equal to 2, goes till n, right, while I is smaller than n, and does I equal to power of I raised to power c, right? So if c is 2 and n is 32, it's going to run for 2, 2 square, 2 square square, which means it's going to run for 2, 4 and 16. Now if you do 16 square again, it's going to become 256, which is going to be greater than 32. So it runs 3 times. Do you see a pattern here? Can you guess the order of growth of this loop in terms of input size? Let us try to find out the number of times this loop runs. So we run the loop for 2 raised to the power c, 2 raised to the power c raised to the power c. We can rewrite this as 2 raised to the power c square, and we can rewrite the last term as 2 raised to the power c raised to the power k minus 1. If k is the number of times this runs, you can notice that it begins with 2 raised to the power c raised to the power 0 and goes till k minus 1, right? So k minus 1 minus 0 plus 1 is k times. Now this 2 raised to the power c raised to the power k minus 1 has to be smaller than n, as our loop says. What it means is, if you take log on both sides, your c raised to the power k minus 1 has to be smaller than log of base 2n. Now we still have k in power, so we need to take the log again. So k minus 1 has to be log base c log base 2n, which means k has to be smaller than log base c base 2 n plus 1. What is this order of growth? You can ignore the lower order term and you can say this code grows this much in terms of input size. So the time complexity of this particular code is theta of log n. Again, base of log does not matter. It can be any base. So the order of growth of such functions where we are increasing a value by doing powers becomes log n. So far we have talked about simple loops. Let us now talk about some complex loops. These complex loops can be subsequent, one after the other. They can be nested, a loop inside other loop, or there can be a mix of these loops. One is subsequent, one is nested. Let us first take a look at simple subsequent loops. So we have this function. We want to find out order of growth of this function. Here we have a loop which runs for I equal to 0 to I smaller than n, I plus plus. So we already know, we have already discussed the order of growth of such loops. So this loop grows theta n times, right? Linearly in terms of input size. This type of loop we have also discussed. How does this grow? This grows logarithmic. So this is theta log n. What about this loop? How much this loop grows in terms of input size? This is a constant loop. It never grows with the input size, right? It does not matter how big the constant is, whether it is 10,000, 10 lakh. When we talk about theoretical analysis, asymptotic analysis, we always talk about n tends to infinite, right? Does it change with n? It does not change. So we consider it as theta 1. That's actually a bad thing about asymptotic analysis. It ignores the high constants, which may matter actually. But that's how it is. That's how the theoretical analysis is. So you have a function which does theta n work plus theta log n work plus theta 1 work. Right? Since they are subsequent, we add their values. Right? When they are nested, we multiply. We'll see the nested example. So what is the value of this expression? You can ignore the lower order terms and you can take the leading term. So you can say that time complexity of this function fun is theta n. You can simply ignore the lower order terms. So it's a theta n function, right? Theta n function. Let us now take a look at this nested loop example. We have an outer loop. How many times this loop is going to run? It's going to run theta n times, right? How many times this loop is going to run? It's going to run theta log n times, right? Because we do j equal to j into 2, right? We have talked about its analysis. So when you talk about nested loops, you simply multiply the number of times this loop runs and the number of times this loop runs. The reason is simple. You have an expression which is going to run multiplication times, right? So your time taken of this function is going to grow equal to multiplication of order of growth of these two loops. So this loop grows theta n times and the inner loop grows theta log n times. We can say that time complexity of this particular function is theta n log n. In theta notations, we can bring this multiplication sign inside, right? So we say it's theta n log n. That's the time complexity of this whole function. Let us now take a look at this code. We have two nested loops. How much is the order of growth of this loop? We have just discussed. It's theta n log n. Right? So this part is theta n log n. And how much is the order of growth of this part? It runs a loop for I equal to 0, I smaller than n, I plus plus 1, j equal to 1, j smaller than n, j plus plus. So this is a theta n, this is theta n. Since they are nested, we say they are theta n square. So this is theta n square. Now what is the overall time complexity of this function? It's theta n log n plus theta n square. So what do we say about the overall time complexity? We can ignore the lower order term and we say it's theta n square. So overall time complexity of this function is theta n square. We ignore the lower order term.